The sixth Gauss-Markov assumption is probably the one that, well, certainly it's one that's always violated, but it's one that has probably been applied differentially to different statistical procedures or to various statistical procedures based upon how popular they are. So one is we know that this is an assumption of ordinary least squares, that all variables, both predictors as well as the criterion or dependent variable, are measured without error. The same applies to principal component analysis, and that's why many people deride principal component analysis, because they say that the assumption is that all variables that go into the PCA model are measured without error. That obviously becomes a problem because in social science, we don't have any variables without error. And why is this such a problem? Well, it's a problem because with measurement error comes attenuation of effects, right? So the simplest way to look at this is probably through a little applet. So here's the URL if you want to try this at home. This is the URL for this little applet. You have to have Java, so it's easy enough. But now we have two scatter plots. On the top is the original scatter plot. This is exactly what we would see given the data as it was intended. And then down here, what I'm going to do is I'm going to modify it by changing the standard deviation of x. Now, why is that? Well, what we're doing is, I need to go over this just a little bit. One thing that we know about from classical test theory is the observed score is equal to the true score plus error. So anytime the observed score, and this is in terms of variance. Okay, so this is variance. So the observed score always has more variance than the true score, because the observed score is a function of the true score variance plus error variance, and they're additive. And so as we add more variance to our true score, the reliability goes down. And the easiest way to look at this is reliability, and typically some Greek letter like rho, which is that weird looking squiggly p. Reliability is equal to the true score over the observed score, which is also equal to the true score divided by the true score plus error. Now you can see this where error variance, as we increase the error variance of any variable, what happens is the reliability decreases, because what we're doing is we're adding e to the denominator. So we're adding it to this true score. And so if I have something like this, where if I have reliability and if I have one part true score and one part error, that would be this, right? So I would include one part of true score and one part of error variance. And when I increase the error variance, what I'm doing is I'm decreasing the reliability. So here is a simulation, and what I'm doing is, you can see here the standard deviation of x and y are both 10. So what happens if I if I include the standard error of x to include an extra 10? Okay, so what I'm doing is I'm decreasing the reliability of x, because remember, this is the standard deviation, and because it's matched by standard deviation, even though my formula here related to variance, we can do one part to one part. So I've included the same part of error variance or standard deviation of x as was observed originally, and you can see now my modified x increases in its standard deviation, as well as, look at the reliability now. Remember, it's one part to one part. So the reliability of x is 0.5. Now what happens? So let's just take a look at it. It attenuates. The original correlation was around 0.9. So now we have a decreased relationship between x and y. Similarly, the slope flattened out. So this line of best fit flattened out. Okay, so it went more towards 0. We went from 0.9 to 0.05. The y-intercept changed a lot. So you can see we went from about 0, pretty close, minus 0.4, to 21. So that's a big increase. That's a big change in our y-intercept. And here, these are just the standard deviations. And this is the standard error of estimate. Remember, we calculated the standard error of estimate in the first week. And what that's telling us is that there's more error involved in estimating this model. Now, what happens if we do the same thing with y? So now we're decreasing the reliability of both x and y. This was our original plot up here. And look at our modified scatter plot. So what are we doing? We're taking our 0.9 and we're cutting our correlation coefficient down in half because we had a correlation that has attenuated because of, this is an attenuation due to unreliability. And you'll notice here the reliability of x and the reliability of y are both 0.5. These reliabilities serve as the upper bound for any correlation coefficient, not just the correlation coefficient, but the coefficient of determination, okay? So if you take Pearson's R and square it, that is going to be the highest value you're going to be able to observe given the reliability of any one of these variables, okay? And we're going to talk about this a lot, but remember, the reliability is a squared coefficient. So in order to get, and remember, reliability is the amount of variance that is reliable. If we go back to this, it is the proportion of reliable variance to the overall variance, okay? Because reliability is equal to the signal over the signal plus the noise. Well, the noise is error, and the true score is the signal. So here we have a ratio, and that ratio means that we have only 50% of reliable variance in x and 50% of reliable variance in y. Therefore, if I go back to this one, I only have 50% reliable variance in x. Actually, I'm going to change this around. I'm going to move this to 10. Whoop. And I'm just going to make y to be less reliable. So y only has a reliability of 0.5. The upper bound for Pearson's R is about 0.7. Now, why is that? Because the reliability is a squared coefficient. That tells us how much reliable variance in y can actually be predicted by any variable, whether it's x or a, b, c, or anything. And so therefore, the upper bound of any correlation has to be the square root of 0.5, because this is a squared coefficient. So we have to take the square, and r is not a square coefficient. In order to find out how much variance is shared, we take r and we square it because we get the r squared, or the coefficient of determination. That coefficient of determination tells us how much shared variance, and reliability is the proportion of reliable variance. So there's only 0.5 that can be actually accounted for, and we account for a good amount of it. Remember, because we started out with an original correlation of 0.9, which is very high. Now, if you look at this, and we'll go back now to attenuating both our predictor and our criterion, you look at here, when both of them are 0.5, we take a severe hit. We take a severe hit in both the slope and the intercept. Remember, we started out at 0.9, now we're at 0.5. The intercept changed a lot. Look at the standard deviations of both x and y. They're inflated, and the reason why they're inflated is we've added error variance. Also, look at the standard error of the estimate. Standard error of the estimate goes up because we're accounting for less variance. As you look at the scatter plots here, look at how it's tightly nested here, right around that regression line. That shows us that our standard error of estimate is small. We're accounting for a lot of the variance. Look at the correlation, right? So we expect an r squared that's pretty high, and it will be. If you take 0.9 and square it, you get 0.81. So 81% roughly of the variance is accounted for in this first regression. When we finish, we have about 0.5, we'll call it. So 0.5, we only have 25% of the total variance accounted for. So measurement reliability attenuates the relationship and adversely affects our parameter estimates. By adversely affecting the parameter estimates, they oftentimes, well, almost always, the betas decrease without question, but the y-intercept turns out to be very sensitive to the reliability. So that's one of the reasons why when we violate the assumption of reliability of our variables in our model, we should take our intercept estimates with a grain of salt, because those are oftentimes extrapolated values. We don't observe values around the y-intercept. And in this case, this is an artifact. So the y-intercept, the fragility of the y-intercept is an artifact of the range of our prediction model. If we had more values that were around the lower end of our x and y variables, that y-intercept would be more robust. That even though we had measurement error, it would deviate, but it wouldn't deviate as much as we're observing. So what do you take from this? Reliability is an essential part of regression parameter estimation, so that we can interpret these parameters and we can generalize those parameters to future models. When we attenuate those relationships due to unreliability, we get parameter estimates that are going to be tied to those reliability estimates. Now, there are researchers and quantitative people who have said there are ways in which we can disattenuate due to unreliability and get more robust estimates. And we're going to talk about this later on in the semester when we discuss path analysis and structural equations modeling. That those are ways in which we can disattenuate the parameter estimates due to unreliability and get more generalizable parameter estimates. So right now we want to look at reliability in our predictors as well as our dependent variables, and that's somewhat misspecified here. Predictors and criterion is more accurate. The next two videos deal with collinearity among our predictors and expected errors, so stay tuned for those.